Welcome to this Maxim Integrated Technical Tutorial. Thanks for taking the time to be with us. Today's topic is the voltage reference, an important element in every electronic design. This tutorial will introduce you to voltage references and will cover the basics on how to select the best voltage references for your designs. Why discuss voltage references? Well, nearly every electronic system incorporates one. Power supplies, both linear and switch mode, data converters, sensing interfaces, all need precise and stable voltage references to operate. Voltage references are available as integrated functions inside an IC or as standalone devices. As a semiconductor company specializing in analog and mixed signal integrated circuits, Maxim Integrated has a rich portfolio of voltage references. In this tutorial, we'll become familiar with voltage references, their construction, and their performance. First, we'll provide an introduction to references and why we need them in real life. Next, we'll focus on voltage references, both Zener and bandgap technologies. The third section reviews the important parameters that determine the quality and performance of a voltage reference. And finally, in the fourth section, we'll showcase two voltage reference products from Maxim. To begin, let's look at the general category of references and their function and utilization in the real world. Any physical system is measured in comparison to a reference, namely an object, system, or experiment that bears a defined relationship to a unit of measurement of a physical quantity. The traditional reference for length for a long time has been a platinum iridium bar stored in a French museum until 1893. Similarly, a platinum iridium cylinder is served as a reference for weight. In the past, people who wanted to calibrate their instruments had to travel to Sèvres, France for the physical calibration of their weight and length systems. Of course, for practical and higher precision reasons, the length reference is today a multiple of a light wavelength emitted by an excited krypton atom. This is easy to reproduce in one's own lab, so there's no longer a need to travel to France. It has been agreed in principle that weight should be defined as a multiple of the Planck's constant. The main characteristics of references are precision, ease of reproduction, and stability versus environmental conditions like temperature, pressure, and aging. In the electronic domain, parameters such as voltage, current, and frequency are also measured versus reference levels. The simplest use of a reference happens with a mechanical scale. That is, measurement is made by determining the number of reference weights required to balance two plates, as shown in the figure on the right. You can see the importance of precision and stability. Could be your diamonds on that scale after all. On the left is a symbol of an electronic component comparing voltages. When at equilibrium, the scale will oscillate gently, while the electronic comparator's output swings in response to the slightest variations will be more pronounced due to its very high gain. Many systems need references in order to yield stable and precise values in operation. One example is body pressure. For wellness, you want your body pressure to be contained between a maximum and a minimum value. Another example is pH. Acidity or alkalinity is measured by comparing the color caused by a chemical reaction using an agent which is sensitive to pH level. The pH must be close to 7 if you want to avoid bacteria in your swimming pool. A final example is silicon wafer production. In wafer fabs, the pressure must be higher than the atmospheric pressure in order to prevent dust penetration into the clean room. Let's now enter specifically into the electronic domain, where the voltage reference is ubiquitous. We'll review various technologies and architectures and discuss their trade-offs. The diode is the very first small, inexpensive electronic structure that provides a relatively stable voltage, that is, the famous 0.6 to 0.7 volts between its anode and cathode when forward biased. As a voltage reference, the p-n junction is sometimes sufficient for simple designs, but its output varies quite a lot with temperature, about -2 millivolts per degree centigrade, and it's also highly dependent on bias current. For example, a 600 millivolt diode at ambient temperature reduces to 400 millivolts at 125 degrees C. That's a 1/3 drop in voltage. Let's talk about Zener diodes. Any p-n junction in reverse bias mode, where the cathode is more positive than the anode, is normally non-conducting. However, if the reverse bias voltage, shown as Vn in the figure, exceeds the threshold, shown as Vz, the junction reaches the breakdown point. At this point, the device exhibits a near constant voltage and a very low series resistance, illustrated in the figure on the right. In this condition, the current grows uncontrollably and is limited only by the external bias resistor R. The breakdown in heavily doped silicon junctions is due to the Zener effect of quantum tunneling of electrons through the junction and yields low voltages in the sub 10 volt range. Lightly doped silicon junctions break down at higher reverse voltages. Under a high electric field, the free electrons are accelerated and hit more electrons in their path, energizing them in turn. This creates a chain reaction or avalanche mode. Although the breakdown mechanism is different for high versus low voltages, these devices are all referred to as Zener diodes. Commercial reference Zener diodes are available from a few volts to a few hundred volts. Zener breakdown occurs easily on the base emitter junctions of NPN transistors at voltages around 4 to 8 volts, depending on the dopant's concentrations. Any integrated or discrete transistor can be configured as a Zener voltage reference as shown. While the Zener effect happens between base B and emitter E, leaving the collector C floating would force a high current through the base high resistance, which would degrade the resulting voltage reference accuracy. Shorting the collector to the base allows the current to flow from emitter to collector with only a small current going through the base. Zener diodes can be fabricated easily in a planar process, where all active junctions are on the silicon surface, which is easy and inexpensive, but such devices suffer from external contaminations and crystal dislocations that are all contributors to voltage instabilities. A solution to the problem is the buried Zener, in which the Zener junctions are created far, that is, several micrometers, below the silicon surface. This way, a very accurate low noise and low temperature coefficient reference can be achieved. Zener voltage references have great performance, but have many limitations, such as higher supply voltage. The simplest voltage reference is the two-terminal Zener diode biased with a resistor R to the power supply VCC. In this configuration, the reference is necessarily in parallel to the load, hence shunting it. The shunt reference lends itself easily to building a negative reference. Bare-bones Zener shunt references have generally good performance, but require high input voltage and have limited drive capability. In the presence of a constant load, the shunt device has low power dissipation, as the load current completely bypasses the reference. In the presence of a variable current, the shunt regulator's resistor has to be sized for peak current, forcing the excess current during light load into the IC and resulting in wasted power. Buried Zener technology, as exhibited in MAX 6325, has best-in-class accuracy and temperature coefficient. The bandgap voltage reference is based on the bandgap energy of silicon, which is 1.12 electron volts. The corresponding bandgap voltage is 1.205 volts. The bandgap voltage is the voltage potential that an electron in the valence band must overcome to move freely and conduct current. The silicon bandgap voltage is temperature invariant. Perhaps not surprisingly then, when we search for a temperature invariant voltage, we find the bandgap voltage reference. Bandgap voltage references, or BGR, are the standard reference in integrated circuits due to their ease of integration, manageable value, typically 1.2 volts, and high performance. BGRs are built with standard IC components, that is, transistors, resistors, and amplifiers, hence they don't add cost or complexity to the fabrication process. A basic silicon BGR yields a 1.2 volt output with a very small tempco. Higher reference values, for example 2.5 volts or 5 volts, are obtained by amplification of the basic 1.2 volt value. We previously mentioned the most disruptive parameter of a voltage reference, which is the temperature. The bandgap voltage reference solution to the temperature problem is simple. You can combine the voltages for CTAT, which is complementary to absolute temperature, and PTAT, which is proportional to absolute temperature, to obtain a relatively flat voltage versus temperature behavior. Let's see how we can do this. First, let's start by building a CTAT. A simple PN junction will do, such as a diode or BJT base emitter. The VBE voltage, as we know, decreases with temperature at a rate of -2 millivolts per degree C. Now we need an increasing voltage, the PTAT, to compensate for this decreasing VBE. The difference between the VBE of two identical transistors biased at different currents is also known as delta VBE. Luckily, delta VBE is perfectly proportional to temperature and yields a positive tempco, equal and opposite that of any VBE, when its magnitude equals that VBE magnitude. Hence, summing up equal quantities of VBE and delta VBE yields a temperature invariant voltage, exactly what we want. Delta VBE can be obtained only in small values, around 18 to 60 millivolts. Thus, we must amplify the initial delta VBE by a constant factor of K. A typical value for delta VBE is 60 millivolts and for K is 10. The next example will further illustrate this concept. As always, in practice things are a bit more complicated. The math is more complex, and a lot of effort in process optimization and design simulation are necessary to obtain a bandgap voltage reference that has minimum variation over temperature. Here's an illustration of the PTAT plus CTAT principle. In the diagram, R2 sees the VBE difference between T1 and T2, which is our PTAT. The current in R2 also flows through R3. Hence, the voltage across R3, or VR3, is also a PTAT voltage, but it's properly amplified by a factor of K, or R3 divided by R2. The voltage drop VR3, which is equal in magnitude to VBE3, is added to VBE3 by placing it on the base of VBE3 to form the bandgap voltage reference VBG. The op-amp amplifies the bandgap voltage VBG via the resistor divider of R5 and R6. Vref can now be a bandgap voltage reference of any value equal or higher than the basic 1.2 volt VBG. R4 is the bias resistor providing current to the bandgap voltage reference. We've seen that the Zener diode is a shunt voltage reference. A shunt voltage reference can also be built with a bandgap voltage reference. A monolithic shunt reference can work with the input power supplies, VCC, higher than its process breakdown, since the IC is isolated from the power supply VCC by the bias resistor R4. In the figure, the reference element BGR is buffered from the load by the amplifier A and pass transistor, allowing for high drive capability. The resistor divider R1 and R2 allows for different values of Vref, including Vref equals VBG with R2 open, in which case D equals 1. MAX 6138 is an excellent example of a two-terminal shunt voltage reference. Housed in a sub-miniature SC70 package with a 1.8 mm by 1.8 mm footprint, it's 50% smaller than comparable devices in SOT23 packages. To learn more about shunt voltage references, please see the related resources section at the end of the video. In a series voltage reference, the load is in series to the Vref output. Hence, there's always power dissipation inside the IC, proportional to the product of the load current with the voltage across the pass transistor T. The device directly connected to the power supply VCC has superior power supply rejection. Here again, the reference element BGR is buffered from the load by the amplifier A and pass transistor T, allowing for good drive capability. The resistor divider R1 and R2 allows for different values of Vref, including Vref equals VBG when R2 is open, in which case D equals 1. MAX 6010 is an excellent example of a bandgap series voltage reference housed in a small 3-terminal SOT23 package. To find more on series voltage references, refer to the related resources section at the end of the video. If your requirements for accuracy, temperature, and noise aren't severe, and you need high current capability, you should consider low dropout linear regulators. The MAX 1589A has plus or minus 1% accuracy over temperature and 86 microvolts RMS noise at 10 milliamps and the bandwidth of 10 Hz to 100 kHz. A graph of typical output voltage accuracy versus temperature is shown. This graph shows plus or minus 0.3% accuracy from minus 40 to plus 85 degrees C. For high current and high accuracy, the best option is to match a good voltage reference to a buffer or power amplifier. Such a solution has the advantage of keeping the reference separate from the heat generated by the load current. For more on LDOs, please see the related resources section at the end of the video. So the question remains, which voltage reference should you choose? It depends partially on the load. In the presence of a constant load, the shunt device has lower power dissipation as the load current completely bypasses the reference, so here the shunt wins. However, in the presence of a load with current peaks of short duration, the shunt regulator's resistor has to be sized for peak current, forcing the excess current during normal load conditions to be taken by the IC. This results in high power dissipation inside the IC, so in this case, a series regulator is preferable. It also depends on the input voltage. For very high input voltages, the shunt regulator wins, as it is current driven via a resistor, hence it's never exposed to the input voltage. For very low input voltages, such as with single lithium-ion cells, the series regulator wins as its architecture takes less headroom. For a negative voltage reference, the shunt reference wins because its bias resistor can easily be placed between the IC ground, now minus Vref, and minus VCC, resulting in a reference properly referenced to the system ground. The analogous minus trick played on a series regulator would result in a reference referred to minus VCC, not system ground. You might ask, should I use a Zener? Use a Zener for the highest stability over time, assuming small temperature variations. Also use a Zener for very high performance if you can afford thermal stabilization by means of circuitry or oven. You can't use a Zener in low voltage applications. For example, a cell phone powered by a lithium-ion single-cell battery varying from 4.2 to 2.4 volts. Finally, should you use an LDO? The answer is yes, if your requirements for accuracy, tempo, and noise are not too demanding and you need high current capability. For more on this subject, please refer to Maxim's tutorials number 4003 and 719. Now we'll discuss the characteristics that define the quality of a voltage reference. Our data sheets characterize the performance very accurately by means of many important parameters. In this discussion, we'll cover the most important of these parameters. Let's start with the output voltage accuracy. This is the output voltage measured on an off-the-shelf device at the beginning of its operational life. It must be within the initial accuracy tolerance reported in the datasheet. Usually it's defined at room temperature and nominal input voltage. Output voltage variations are usually expressed in plus or minus % of the nominal voltage in the datasheet. But depending on the application, this parameter can be expressed in parts per million over temperature, for example, or number of bits of resolution for data conversion applications. Let's use MAX 6033 as an example. The A version, MAX 6033A, has an initial accuracy of plus or minus 0.04%. On a nominal reference of 3 volts, that means that VOUT can be any value between 3.0012 volts and 2.9988 volts. The total deviation value is plus or minus 1.2 millivolts, or 400 parts per million, or 11 bits. There are many causes for the output voltage spread. Variation in the fabrication process and packaging stress are the main ones. It's important to note that output voltage error can be calibrated out in hardware or software when a pin for this purpose is available, thereby considerably improving the native accuracy of the reference. However, in doing so, you may have to accept a degradation of the IC temperature coefficient, as the external trimming resistor's tempo will likely not match the internal one. Use of sensing and forcing pins helps avoid additional errors from parasitic voltage drops in the PC board. Minimization of the board's mechanical stress and maximizing board cleanliness all help accuracy. For more on this subject, please refer to Maxim's tutorial number 719. Another important parameter is output voltage temperature coefficient. Temperature is the main cause of reference voltage drift. The temperature coefficient gives a measure of how the voltage reference changes over temperature. It's often referred to as TempCo, labeled TCVOut in the datasheet, and expressed in parts per million per degree C. TempCo is specified with the box method, namely a box is formed by the min and max limits for the nominal output voltage over the operating temperature range. In the example shown, all MAX 6071-12 units will be contained in the purple box, plus or minus 1320 ppm, while the single unit in the picture exhibits a variation of only plus or minus 0.15 millivolts or plus or minus 125 ppm. Since the voltage reference variation with temperature is nonlinear, the local temperature variation along the curve, the local tangent to the curve, expressed in parts per million per degree C, can be very different from the min and max values reported in the datasheet. For example, If in the datasheet the tempco is plus or minus 8 ppm per degree C and specified between minus 40 to plus 125 degrees C, you can't predict that when going from 25 to 50 degrees C, the deviation will be contained within plus or minus 25 times 8 or plus or minus 200 ppm. All we can say is that a single MAX 6071-12 unit can have any amplitude and shape, but is always contained within the plus 1320 minus 1320 ppm box. Tempco can be improved by means of thermal stabilization, whereby the full swing of ambient temperature is countered by means of circuitry or oven. More on the tempco can be found in Maxim's tutorial number 4419. A voltage reference has two main sources of noise, flicker noise and thermal noise. Let's consider flicker noise first. Flicker, or 1 over F noise, is generated in the presence of a current and expressed in microvolts peak to peak in a bandwidth between 0.1 to 10 Hz. It's specified in microvolts peak to peak because noise over this band is of most interest in DC applications, where peak errors are a primary concern. This low-frequency noise, shown in the graph, is difficult to filter out. One way to reduce flicker noise is to stack up voltage references in series. While the resulting voltage multiplies up by the number of references, the resulting noise only goes up with the square root of that number, as uncorrelated noise. For more on this, see Application Note 3531. How about thermal noise? Thermal noise is generated by random thermal motion of charge carriers regardless of any applied voltage. Thermal noise is expressed in microvolts RMS in a bandwidth between 10 Hz and 10 kHz. It's specified in microvolts RMS rather than microvolts peak to peak because noise specified over a wide band is of most interest in AC applications, where signal to noise ratio is of primary concern. Noise in SNR measurements is given in RMS. Thermal noise is proportional to the square root of the frequency bandwidth of interest. Hence, in the 0.1 to 10 Hz range, where flicker noise dominates, at 0.5 microvolts RMS, thermal noise is negligible, as shown in the numerical example. For a Gaussian distribution noise, the peak-to-peak value will exceed the RMS value by a factor of 6.6 only 0.1% of the time. V peak-to-peak is approximately 6.6 times VRMS. Thus, 0.5 microvolt RMS corresponds to 3.3 microvolt peak-to-peak. Thermal noise is easier to filter out, being at higher frequency. It's important to note that noise affects the initial accuracy. This source of error cannot be calibrated since noise is random. Another important parameter is long-term stability. Long-term stability requires a long test time to measure, 1,000 hours or close to 2 months. The test is performed on a selected sample population under set conditions for nominal Vn, temperature, humidity, and load. Up to 5 complete boards are loaded into an oven for temperature control. Each board has 32 reference sockets populated by 16 samples for each of 2 types of IC. The long-term drift test can't be accelerated by the burn-in techniques allowed by the Arrhenius laws. In this case, the 1,000 hours of testing must be done in real time. Since long-term drift is becoming more and more important, Maxim is extending the test beyond 1,000 hours, at least for the ultra-low tempco and low-power versions like Max 6070. We're also in the process of extending this test to 10,000 hours for selected devices. Please contact us if you'd like to find out more. In addition to temperature coefficient and accuracy, there are other parameters that contribute to voltage reference performance. Current consumption, drive current, supply voltage range, package, and cost are all factors influencing part selection. Let's now take a closer look at 2 voltage references offered by Maxim. Max 6126 is an ultra-high precision, ultra-low noise series voltage reference. It incorporates an impressive combination of best-in-class parameters. It has excellent initial accuracy of plus or minus 0.02% max, sensing and forcing pins which preserve accuracy over load-induced voltage drop errors, ultra-low tempco with 3 parts per million per degree C max, ultra-low noise with only a few microvolts peak-to-peak in the 0.1 Hz to 10 Hz range, and low current consumption of less than 1 milliamp over the full temperature range. Max 6126 is available with several voltage options: 2.048, 2.5, 2.8, 3.0, 4.096, and 5.0 volts, all in small SO8 and Micromax 8 packages. MAX 6072 is a dual output precision series voltage reference featuring a plus Vref and a plus Vref over 2 output. Each output has 2 pins, a forcing pin supplying current to the load, and a sensing pin for precise regulation of the voltage applied to the load. The device has an initial accuracy better than plus or minus 0.08% and a 1/F noise below 10 microvolts peak to peak, and a temperature drift below 8 ppm per degree C. Each output can source and sink 10 milliamps. 3 pairs of output voltages are available: 5 volt with 2.5 volt, 4.096 volt with 2.048 volt, and 2.5 volt with 1.25 volt. The dual outputs make this device ideal for precision ADC applications where the input signal needs to be referred to Vref over 2. MAX 6072 is housed in a small Micromax 10 package with a small 2.95 by 4.78 millimeter footprint. We've covered the basic operation of voltage references and how to select the best references for your designs. I'll now provide you with some resources if you'd like to learn more. To learn more about the voltage references we discussed today and our complete portfolio of shunt and series references, visit the Voltage References resource page on our website at maximintegrated.com/vref. On our website, you'll also find application notes and tutorials covering series versus shunt references, voltage reference specifications, temperature drift, thermal noise, and noise reduction. On our website, you'll also find more about our low dropout linear regulators. Thanks for joining us today. We hope you'll join us again soon for another tutorial or on our website at www.maximintegrated.com.